In previous lectures, we've discussed the effect of the water table on the unit weight of soil, creating an effective unit weight that in turn alters the active earth pressure. Similarly, a high water table will also have a buoyancy effect on the abutment. I like to consider the water table conservatively in these two ways. First, if the high water level is above the design foundation elevation, like in the figure below, I'll consider the temporary effects of the water table in flooding events. And second, it's also important to check the anchor excavation during the construction process for water for a handful of reasons. Some, but not all, include flowing water through the excavation can contribute to scour, effectively moving soil beneath the abutment and causing more settlement. Water in the abutment can cause corrosion to the cables. Buoyant forces acting against the anchor weight are a cause of a high water table. And the sliding coefficient in saturated conditions is different. So scour and corrosion we want to control by drainage systems if this is a frequent issue. Buoyant force we're going to control with our design. We're going to make sure that the design is still adequate under these conditions. And the potential change in sliding coefficient in saturated conditions will be discussed in later lectures on bearing capacity. So if standing water is obvious, drainage should be considered to cover water flowing through and around the abutment. Here we can address that case in which standing water is present or suspected in the anchor excavation due to a rising water table during a flooding event. If this is a temporary event, a one-time, a safety factor of 1.25 is permitted, and that's discussed in the EIA Bridge Binder Volume 2. If this is a long-term event or a seasonal event, a safety factor of 1.5 should be used, and all of the conditions above should be considered. So with that being said, the learning objectives of this section are to 1. Analyze when buoyant forces from a rising water table should be considered. 2. Understand how buoyant forces reduce the effectiveness of gravity anchors. And 3. Calculate new factors of safety for these flooding events. So, we'll start by calculating or examining the effect on uplift of the anchor. So using Archimedes Principle, we have our buoyant force is going to be equal to the volume of the fluid displaced multiplied by that unit weight of the fluid, in this case, water. And our density for water, as you may remember, is 1,000 kilograms per meters cubed. And in this equation, volume is that displaced fluid, in which concrete can be assumed to displace the water 100%, and soil will displace that fluid around 60%. Now, for the purpose of quick and easy calculations here, I'll just assume everything is displaced 100%, but if we wanted to sharpen the pencil, we could take that 60% value for soil. Using allowable stress design, the buoyant forces simply can be subtracted from our force that is resisting uplift, our Vn. So we have our new Vn as our anchor weight, our overburden weight, minus our buoyant force. And for analysis using LRFD, it should be applied with the appropriate load factor and combination. In the case of sliding, we can use the same reduction factor as above for uplift to reduce our vertical forces, but multiplied by a different area. And as you can see below, our new volume of water displaced is going to be that length of the water that is displacing along the abutment, multiplied by the width, multiplied by that same difference between the foundation elevation and the high water line elevation. So we'll get our new sliding resistance as our total vertical forces minus our buoyant force multiplied by our sliding coefficient. And I noticed I put a mu prime here because mu prime can change based on saturated conditions, and if this is going to be significantly different, we need to make sure we're using the new mu prime.